Okay, so here we are writing an acid dissociation constant expression. They ask us to fill in the left side of this equilibrium constant equation for the reaction of acetic acid with water. Now, I do realize that acetic acid here is written very funny. Sometimes you may see acetic acid as CH3COOH or HC2H3O2. And as an acid, it'd be aqueous. But here they write it a little different. They have it as HCH3CO2, but they do tell us that it is acetic acid. And they just write it in this way because we know that this is the ionizable proton for this weak acid. Okay? So what do we do? How do we answer this problem? Well, let's write the chemical reaction equation for this process. So like all acids, acetic acid is going to react with water by transferring a hydrogen ion to it. So we have our reactants. We've got acetic acid written using the chemical formula that they provide. It's an acid, so always remember to write your aqueous there, okay? And it's going to react with water, liquid water, and water here is our solvent. Now, this reaction is at equilibrium, and here we have our acid in this reaction, which is the acetic acid, and here water, which can act as an acid or base, is acting as our base. So what happens when acetic acid reacts with water molecules? Well, acetic acid as a weak acid is going to dissociate. Now, it's not going to dissociate 100%, but it's going to dissociate to some degree. And so what does that mean when acetic acid dissociates? It means that it loses a proton here. It's got one ionizable proton or hydrogen ion, and it's going to lose that, and that proton is going to be picked up by water molecules. So our products here would be H3O plus, that's hydronium, and the conjugate base of this acid, or this weak acid, which would be this. Now, before we do anything else, we need to ensure that this chemical reaction equation is balanced. And when I look at it, it looks to be balanced, so we are good to move forward. So when I look at this reaction, I realize that this is in some equilibrium. And for weak acids, that equilibrium usually favors the reactant side, as long as the concentration of the weak acid in solution is not extremely low. So this is why weak acids are considered to not dissociate 100% like strong acids do, because this process is at equilibrium. So even though acetic acid does lose a proton to water to form hydronium and this conjugate base of the acid, well, this conjugate base, being a conjugate base of this weak acid, means that it will have some affinity for hydronium ions, and it does. And so this reaction also goes in the other direction to produce acetic acid again. So again, this reaction being in equilibrium is going both ways, but the reactant side is favored. If I were to very briefly show you the chemical reaction for the dissociation of a strong acid like hydrochloric acid, it would look like this. And you would not see that the reaction would be in equilibrium, because the products of this, hydronium and chloride ion, this chloride ion here, which is the conjugate base of our strong acid, does not have any affinity for hydronium. And so this reaction, to any measurable extent, will not go back in the other direction. So it's just going in the forward direction, it is not in equilibrium, and so we could safely assume that this process goes all the way to the right to completion. Okay? So we could derive this conclusion from this discussion about strong and weak acids. For strong acids, the conjugate base is weak. In this case, the conjugate base, chloride ion, has no affinity or very, very, very little affinity for hydronium. So that means that this reaction will not go in the reverse to any measurable extent. And so, again, it's just a forward process. However, on the other hand, for weak acids like acetic acid in this example problem, the conjugate base is going to have affinity for hydronium, and so the reaction will go in the other direction, which is what we're seeing here. Again, the conjugate base has affinity for the hydronium ion, and so the proton from this hydronium ion can be transferred back to this conjugate base, and the reaction goes in this direction. So for this acid dissociation reaction, how do we write the equilibrium expression for this ionization? Well, we tackle it just like we did Kc for equilibrium expressions. But because we're talking about the ionization of a weak acid, we're going to use Ka. Ka is called the acid ionization constant, and it is derived the same way that we derive Kw, the ion product constant for the autoionization of water, and also Kc for general chemical equilibrium. So you all already know how to arrange the acid dissociation constant expression with the products on top in the numerator and the reactants in the denominator. Now notice again here that water is eliminated from the acid dissociation constant expression because it is the solvent here and it is liquid state. So because it's present in such high quantities, its concentration is essentially not going to change and it's going to remain constant, so it is eliminated from the acid dissociation constant expression. So this would be our final answer. And if you want to explore a few things about Ka, you may do some reading or watch some videos, and you'll come to the conclusion that as Ka gets larger, then that means you have a stronger acid. Smaller Ka, so if Ka becomes smaller and smaller, then you get a weaker acid. Now what do I mean when I say stronger acid for larger Kas and a weaker acid for smaller Kas? Well, the only acids that have Ka values associated with them are weak acids. Okay? So some weak acids, for example, are hydrochloric acid, or here, acetic acid. So I'll write it the way that they wrote it in this example problem. So those are two weak acids, and each of those weak acids have an associated Ka. But what you'll notice is, if you look up these Ka values, the Ka of hydrofluoric acid is a larger value than the Ka of acetic acid. And so what that means is solutions of equal concentration of these two acids do not have the same pH. The pH of the hydrofluoric solution is lower, which means that the hydronium ion concentration is greater than that of the acetic acid solution. Why is that? Well, because the Ka of hydrofluoric acid is larger. And the larger the Ka, the more the acid dissociation reaction is going to favor your products. And when we're talking about the products from the dissociation of a weak acid, what are they? Well, hydronium and conjugate base. And so because the products are favored, you've got more hydronium in solution, and that is going to decrease the pH more.